All right. And we'll talk about how we are going to upload the homework to the Canvas. But essentially, they're just assignment tab where you can upload your PDF format written file to it. So you might have to find a scanning app on your phone or just find a scanner where you can scan your written notes. Either way, I mean, it works for me. Unless it is not clear enough and you probably can tell before you even upload it. Okay. All right. So let's just get right into it. Okay. A quick recall what we have talked about last time. We gave a short introduction last time about what type of concrete structures there are and what's the basic of the concrete structures in terms of the advantages over steel structures, right? I'm not trying to beat down our neighbors across the hall who's teaching the steel structures, but we need to know what are the advantages of reinforced concrete structures in comparison with steel structures. And in our first exam, we might have one or two questions regarding that. So if you haven't understood that content yet, you can quickly go back and review the lecture content from YouTube and the posted notes. Okay, so today we're going to cover two sections. First of all is the concrete materials properties, right? So what are the most important materials properties in reinforced concrete structures? So namely, there are two. One is concrete and the other is reinforcing steel. If I can have one thing that engrave your brain after the lecture, that should be concrete is good for compression and the reinforcing steel is good for tension. Okay, so that is how the composite action plays. So let me say it again, emphasize the importance of this. That is the concrete is good for compression, okay, and the steel is good for tension. That's how they work together to give you the structure load bearing capacities. Okay. So let's talk about concrete first, right? What are the most important properties of concrete? Now, before we get into it, first thing came in your mind about concrete are two states, right? One is a fresh state when you can mix them using a mixer and you can see it's flowing everywhere. And the other state is where it's hardened, right? Cold and strong and standing there in the structures, right? So the property we are talking about today and in this course will be mainly focused on the hardened concrete. Hardened concrete. So if some of you are taking the construction materials course where people have more interest in fresh state of concrete when it's liquid. Okay, so what are the most important properties or type of properties we're looking for in concrete are these four. First of all is the compressive strength, right? So how much compression can the concrete take? Then also the tensile strength, how much tensile stress can the concrete take? And modulus of elasticity, and if you've taken mechanics materials class already, and I thought you should have done that already, it is the Young's modulus, right? Between the stress and strain, between the stress and strain. And the last but not least is a volume change, okay? The volume change means shrinkage, means creep, means permanent volumetric change of the materials, okay? So these are the four critical properties for concrete. All right, so before we get into that, let's take a quick look at the composition of the concrete material itself. So we have observed the earliest structure, reinforced concrete structure back in the Roman times, right? Where people used two type of materials to form this concrete base, which is the paste and then the aggregates. So if you really think about the mechanism, how concrete materials give us the strength, it comes from these aggregates or little pebbles are glued together, right? Glued together by this viscous, adhesive, cohesive materials. So you can think of it as a bunch of bunch of aggregates that glue together to give you the strength of concrete. Okay, so what are the typical paste materials? Okay, now the two commonly seen paste materials here are Portland cement and porcelain, right? So both are cementitious materials, meaning when they see water, they react, they hydrate, and they form very hard crystalline structures and basically acting like a glue to glue those aggregates, the rocks together. Okay. Now, the other most important component, of course, that is water. So we have these dry cementitious materials. When they meet water, they react and form the glue you're seeing. Okay. Now, for the coarse aggregates, right, we're talking about gravels, right? You can probably see them from the pit where people actually crush rocks, right, and give you the gravels from the quarries, from nearby the sandy rivers. And you also have the crushed stones where people take big giant granites from the mountain and they crush it into little pieces. And these are the coarse aggregates that takes care of the main component of the compressive strength of the concrete. Okay, they are the cornerstone of the compressive strength of the concrete. And the other type of the aggregates is the fine aggregates, where are river sand, right, other filter sand particles. And the purpose of these fine particles are A, to fill in the void in the structures, B, carry the water because it has a lot of surface pores where they can absorb a lot of waters, and to maintain the moisture can play a significant role during the hydration process. Okay, during the hydration process. All right, so now we have gone over the basic components of the concrete, the paste, the aggregates, and in the paste or a cementitious material, there's water, and in the aggregate, there's a coarse and there's a fine aggregates. So what are the proportions, right? It's like a recipe. What are the distributions in terms of weight percentage, volume percentage of the concrete, right? So here are the distributions. So the paste roughly constitutes about 25 to 40% of the total volume of concrete. So it's quite significant, right? The absolute volume of the cement is usually between 7% to 15%, and the water is typically between 14 to 21%. Now, the air content, the air entrained concrete ranges from about 4 to 8% of volume. Now, some of you might say, okay, why do we need air? So the air bubbles help the concrete flow. Okay, the air bubbles help the concrete to flow. And then the aggregates makes up the 70 to 60 to 75% of the total volume. They are the most volumetrically important part of the materials. Okay, so selection of the aggregate is quite important. Any deleterious, which are bad aggregates, have chemical elements in it that can easily react with water and other components, can be bad to your concrete. So selection aggregates can be very, very important. Okay. Now aggregates should also consist of particles with adequate strength and resistance exposure conditions. So should not contain materials that will cause any deteriorations, right? And the continuous gradation aggregate particle size is also important. And you will learn that from the materials, construction materials class. That is, the proportion of different sizes aggregates inside the concrete also plays a very important role in terms of aggregate interlocking, shear strength of the concrete, and so on and so forth. Okay, so these are the composition of the concrete materials. All right, now we also want to talk about the concrete components, right? First of all, let's talk about the quality of the hardened concrete. Okay, so the quality of hardened concrete is strongly influenced by the amount of water used in relation to the amount of cement. Usually, high water cement ratio, meaning you have a weak concrete, low water cement ratio when you have a high strength of concrete. However, there's a problem related to workability, meaning if you have a too water-ish concrete, it's easy to work with, but very low strength. If you have a very low water content concrete, it is damn hard to work with, but it is very strong. It is very strong. Okay, so there's a limitation about the water cement ratio where you learn more in the construction materials class. Okay, construction materials class. All right. So what are the other concrete components, right? So there are advantages of reducing water content. We're talking about this, right? The increased compressive flexural strength by increased cementitious strength, the lower permeability because it reduced the void content, and increased resistance to weathering. Again, it increases the tensile strength, hence increases wear resistance to weathering, and have a better bonding between concrete reinforcement. That is the stress that can be transferred from concrete to steel or from steel to concrete is higher when you have a lower water cement ratio. All right. And again, with lower water, you have less shrinkage. So you have less drying shrinkage and also cracking. And last of it is less volume change from wetting to drying because again, less water contents there are. Okay. So In short, right, the less water it uses, the better quality of a concrete, but they'll hurt the workability. Okay, so to manipulate the concrete properties to the extent that we can easily work with, there are several ways to go at, right? So the one of the most efficient ways to use admixtures. These are chemical agents we can put into the concrete properties to change it towards our needs. For example, we can use air entering admixtures, basically put chemical component to it, it can generate air, and we can use water reduce admixtures. So when we work with a concrete, it still flow, but as time goes by, it can reduce water by absorbing chemical absorption or physical absorption. We can also add plasticizers, making concrete more flowable, accelerators that accelerating the hydration process, and retarders to slow down the hydration process, okay, to enhance the time, increase the time that we can work with the concrete. So these are basically chemical magic we can play to change the property of the concrete. And does not limit to that. We also have corrosion inhibitors where we can reduce the water permeation through the concrete cover. We also have the shrinkage reducers to reduce the shrinkage, and alkali silica reactivity inhibitors to prevent the alkali silica reaction, which is pretty bad in Arkansas and some of the other states in the Midwest area. And also we have a coloring to make the concrete aesthetically more appealing. And we have also other admixtures to make the concrete into the properties we want them to have. Okay, so in short, there are a lot of chemical components that we invented can be utilized to tune the properties of the concrete towards our needs. Okay, all right. So in addition to those, there are descriptions and requirements for the properties of both concrete and steel reinforcement in the code. Okay, in the code meaning the building code of ACI 318 and 19. And by the way, if you still haven't found a way to purchase them, talk to me after class or through email. You need to have 1 copies of the code, okay, to be able to work on this class. Okay, so these are the chapters related to the properties, chapter 19 for concrete and 20 for reinforcement. Okay. All right, so let's talk about concrete first. In our course, of course, this is about hardened concrete, dried and tough concrete, right? So if I compress concrete and I take the stress versus strain relationship, and you learn that from mechanics material, right? That's the basic materials property of the concrete in compression. And this what the curve looks like. You have a linear response at the beginning and get into a little bit nonlinear hardening behavior. Hardening means that the increased strain indicating a gradual nonlinear increase of stress, then to a peak stress where I reach the maximum strength of the concrete and then gradually crushing it, have micro cracks, and eventually fail the concrete. Okay, so this is the compressive stress strain curve looks like for concrete. All right, and to get this curve, we usually use the cylinder, right? The concrete cylinder, the cylindrical compressive test, right? And there are 2 standard. One is ASTM C31 and the other is ASTM C39. Both are compressive strength testing for concrete cylinders. The only difference is the size, right? So we deal with either 6-inch concrete cylinders in diameter and 12-inch in height. This is big concrete cylinders. We also can deal with 4-inch by 8-inch concrete cylinders, right? So these are the typical standard concrete specimen we use for getting the compressive strength. Okay, that is F prime C, F prime C. All right, so when we talk about the compressive strength, again, right, it looks simply just like this. We have a linear response and we have increased behavior and we have a peak strength and goes down about it, right? Goes down about this curve. But what are the critical parameters we need? What are about the critical parameters we need, right? And we need the peak strength, which is right here on the top. And this is called the F prime C. Okay, and this symbol has been there in codes and everywhere, right? So whenever you see F prime C in this class, that means the compressive strength of the concrete, the highest stress concrete can take under compression. All right. Now we all know that concrete can be hydrated, right? It can cure, right? If you've seen a job site, most of the concrete be covered by burlap with water on it to cure it, right? So the concrete is expected to reach the best, highest strength at 28 days. At 28 days. Okay. So you have F prime C. This is corresponding to the 28 days, right? 28 days strength. Okay, it's the concrete compressive strength at 28 days after it's poured. Okay, but for other type of concrete or high strength concrete, right? When we're talking about high strength concrete, we usually talk about the compressive strength exceeds 6 ksi, right? Range between 6 to 8 ksi. This is high strength concrete. It takes a longer time to cure. So the F prime C can usually be attained for the high strength concrete at 56 days, 56 days, even sometimes 90 days. Okay, even sometimes 90 days. All right, so this F prime C is critical. It's critical for our compressive strength of concrete, and we use all the other parameters, right? We use all the other equations, right, based on this parameter F prime C to represent different attributes of the concrete. Okay, so first let's take a quick look at it, right? So with different concrete strengths, the curves looks different. As lower the strength goes, you have more flat curve. Higher strength, you have a sharp curve. What does it mean, right? It means that lower strength concrete have a better ductility because it can sustain a lower pressure to a longer strain, but have a higher strength is more brittle. Is more brittle. Okay, so we need a lot of steel reinforcement for actually high strength concrete because it is brittle. All right, it's brittle. Okay, so now let's come back to this compressive stress strain curve again. We have this nonlinear curve and the peak strength F prime C. We need to know the Young's modulus, the Young's modulus. So how do we define the Young's modulus, right? How do we define the Young's modulus? So there are several ways to define Young's modulus. If I draw a dashed line, which is this red line here, as a tangent of the linear portion of the response, and I can call it initial tangent modulus, initial tangent modulus. Okay. Now, if I draw another tangent modulus at any arbitrary point A, for example, here, this is called the tangent modulus at stress A, at stress A. Okay, but none of these two instant initial tangent modulus nor the tangent modulus at any arbitrary point, none of these two is the modulus we talk about. The modulus elasticity we talk about is typically the secant modulus, right? Secant modulus as a particular strength, as a particular strength. Okay, so that is called Young's modulus EC. Okay, that is called Young's modulus EC. So you may start asking questions. So Bob, I don't know. How do I find Young's modulus EC? ACI actually have equations for you, right? In chapter 19, and it's an equation 19.2.2.1a, it tells you what are the relationship between the Young's modulus EC and the compressive strength F prime C. Now there are two equations. The first equation is I have a omega C, which is the density of the concrete between 90 and 160 pounds per cubic foot, right? Cubic foot. That is omega C to the power 1.5 multiplied by 33 square root F prime C. And keep in mind that inside the square root, F prime C is in PSI unit, okay? If you put in the KSI, you get a round number, all right? So it has to be in the unit of PSI, okay? And for normal weight concrete, basically you don't know omega C, or omega C is typical, which is 150 pounds per cubic foot. You end up with EC equal to 57,000 square root of F prime C. Again, the unit for F prime C is in PSI, okay? PSI. All right, so these two equations are very important. You will need to remember them, okay? You need to remember them for your homework and the first exam. Now, the first equation is hard to remember a little bit, and the second equation definitely should remember it, okay? 57,000 of square root F prime C. All right, okay, so these are the relationship between the modulus elasticity, which is EC, and the compressive strength, which is F prime C, okay? Keep that in mind. All right, so that is the compressive strength of concrete. How about the tensile strength? How much tensile stress concrete can take? So the tensile strength of concrete varies between 8 to 15% of the compression strength of the concrete. Okay, but how do we get the tensile strength of concrete? So unlike the compressive cylinder test, we get the compressive strength. We use the beam testing, and they call it modulus of rupture or flexural test. This is a simple illustration of flexural test. We have a 3-point loading. That is a beam. It's sitting on 2-point load, simply support a case, and apply force in the middle and try to crack it. And upon its cracking, I have the maximum force And sorry, maximum moment, I can use that to compute my flexural strength using these beam equations. Fr is called the modulus of rupture, which is equivalent to the tensile strength of the concrete, equal to 6 times of the moment at rupture, which is m, divided by the BH squared. Okay, so I got a question about what was that omega, all right? And let me go back to one slide, sorry. So omega right here, omega C is the density of the concrete. Okay, the normal density of the concrete is 150 pounds per cubic foot, but in the equation, this equation 19.2.2.1.8 applies when your density is between 90 to 160. Okay, so you can use this equation, but it is the second equation, 57,000 FRMC, is the most used equation. Okay, so the second equation is mostly used equation. All right. Okay, I hope that is clear. Okay, so let's move on. Now, we can use the 3-point bend test to determine the modulus of rupture, which is tensile strength of concrete. Okay, so that's the standard test. But they're not only limited to the 3-point bend. Okay, so the single beam with third point loading or 3-point bend is the ASTM C78 standard. Okay, but there's another testing standard, which is a center point loading. Okay, so the top is the third point loading where I have 4-point bend, and the bottom here is a center point load, which is the 3-point bend. So apologize, I made a little bit error here. So the center point loading is the 3-point bend, right? You have 1 point in the middle, 2 points on the outside, so I call it 3-point bend. And the third point loading, which is actually a 4-point bend, which have a 2 point on top and the other 2 point of support. Now, these distance between the loading point to the support, okay, is half of the half span, okay, it's quarter of the whole beam length, okay, so that is the difference. So some of you may ask, hey Bob, what's the difference? I mean, they look same to me. The difference is that in the 3-point load, which is the bottom here, I only have the maximum bending moment in the middle. I have a maximum bending moment in the middle. But in the top here, I have a constant moment, all right? If I draw it here, I have a constant moment. Okay, so this is so-called a constant moment region. Okay, if you learn from mechanics materials, the whole section have a constant moment. Okay, constant moment. I need to practice my drawing because I'm using my mouse. I'll use the pen next time, sorry about that, but this is the constant moment region, okay? So the difference between the top and bottom also, because I have a constant moment region, I tested more volume of concretes. So I have more statistic variation. So I have a lower strength on the top. I have a more higher strength or larger statistic variation using the bottom. So if you have facilities, if you have the proper equipment, I suggest you go for the top one, which give you a more of a average representation of the tensile strength of concrete. But if you don't have, you can go for the latter one. Okay, so that is the major difference here. That is the major difference here. Okay, all right, moving on. Let me go to the next slide. Oops, things frozen. What's going on? Okay, I need to probably get this one out. Okay, sorry about that. All right, glitch. Okay, here we go. Moving on, that's not the only test to get the strength of concrete, okay? And be careful, for this beam bending test, right? We call it FR or modulus of rupture, all right? Modulus of rupture, and we use the symbol FR, okay? Use the symbol FR. But there are other ways to test it, and this is called split cylinder test. So under circumstances, typically in the field, it's very hard to find good equipment to perform the bending test and to make the beams, right? It's very hard sometimes. So we use the cylinder for compressive strength to get the split cylinder test because they're easy to make, right? Just need a bucket with the same size, and you can make it, right? And how to test is that we have a support underneath of the cylinder, so they're kind of like a bending case, and we have a line of loading. So if you've seen this, it's more like a block, like a rectangular long piece of prism or a block sitting on top of a cylinder, and just apply a compressive force, right? P here. And Given a diameter of d, and I can use my mechanics materials knowledge to find out the stress distribution along the loading direction is more like a compression at the top, local compression. Then I develop a tension and this uniform tension across the section, then go back to the compression. Okay, so it will fail in the middle because I have the tension developing in the middle. All right, it's kind of like a truss structure. I compress at both sides of it and the bust in the middle. Okay, bust in the middle in terms of tension. All right, so the testing failure looks like this, right? When I have a compression sitting on top of it and I have a fracture throughout the cylinder, okay? This is called a successful test, okay? And these are truss structures internally to show you the loading path distribution, all right? And there's an equation to give you the relationship between the tested tensile strength FCT equal to 2P over pi LD, And be careful, this is called the split, okay, the cylinder split test, sorry, the split cylinder strength, CT here. So FCT is different from modulus rupture, okay? And typically FCT is lower than FR, okay? Typically FCT is lower than FR, all right? So we can play a split cylinder test, and give me 1 second. Let me share my screen with you so you can see it. So stop sharing and share screen. And here is a split cylinder test, right? So I have 2 wood shams at the bottom and top of the cylinder, and this red line here is the expected failure line or center line. So I keep loading it. I'm sorry, there's no volume audio, okay? But as I keep loading it, you should start seeing fractures in vicinity of this red line here, okay? You should start seeing the fractures in the vicinity of the red line here. And a quick question, I just want to pop up in your head that what type of failure that is. It's going to be brittle, it's going to be gradual, it's going to be brittle, right? It's going to be brittle. So quick failure. Once you start see crack develop, it propagate all the way through. Okay, so it's pretty safe, right? It's pretty safe test. Okay, so let me stop sharing and come back to my screen. Where is it? Okay, so that is the split cylinder testing to get the tensile strength of the concrete. Okay, get tensile strength of concrete. All right, so we have talked about the compressive and the tensile strength of the concrete. So there are a relationship, right, between the tensile and compressive strength, because an old seasoned engineer can pretty much tell the tensile strength of concrete if knows if the compressive strength of concrete is known. All right, so then the tensile strength is proportional with the compressive strength. So tensile strength increases where compressive strength increases. And B, the ratio of tensile strength compressive strength decrease as the compressive strength increases. You can think of this way: if I have a high compressive strength, my tensile strength will be capped. Okay, my tensile strength will be capped. It will not grow infinitely together with the compressive strength. And last but not least, the tensile strength is actually proportional to the square root of F prime C. Okay, so that's an empirical relationship. How do we get this, right? So we test a lot of compressive strengths, and we test a lot of tensile strength for the same concrete materials, and we plot them and find out the relationship between them is typically in terms square root of F prime C. Okay, and specifically, these are the relationship, right? So from empirical testing results, we find out that the split cylinder tensile strength, which is FCT, roughly you could do 6.4 times of square root F prime C. And the modulus rupture a little bit higher, which is about 8.3, okay? Which is about 8.3. However, for deflection calculation point of view, we use different. And sorry about this is typo, okay? It should be ACI 318.19, okay? And this equation number is correct, it's 19.2.3.1, okay? However, though, this FR, which is modulus rupture, is usually taken as 7.5 lambda square root of F prime C, okay? Lambda square root F prime C. Let me make an annotation here. This is very important, okay? We will test you in the exam and we will test you in the homework, okay? Very important, okay? 7.5 lambda square root of F prime C, okay? And now, what is this lambda? Now, lambda is a weight or density coefficient. It's usually 1.0 for normal weight concrete, NWC, okay, normal weight concrete. But for a lightweight concrete, oh, I'm so sorry. Let me go back. For lightweight concrete, okay, lambda usually equal to 0.75 for lightweight concrete, okay, for lightweight. So for, okay, I will learn this. Trust me, give me time, I'll learn this. LWC, okay? My horrible drawing, LWC, okay? It's 0.75 for LWC. So you may ask a question, okay, but what is lightweight, right? How do you know it's lightweight? So the question to that is, let me clear my drawing and go back to the previous slide. You remember we talked about the Young's modulus relationship with F prime C, and there is a criterion all the way, boom, 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 right here. See that the omega C between 90, 160 pounds. So this is a range of normal weight concrete. Okay, range of normal weight concrete. Below the 90, yeah, that's low lightweight concrete. Okay, that's a low density lightweight concrete. Okay, so there are some criteria we introduce later along the course, but that's something we have to pay attention to. And don't worry, in the exam, we'll tell you, right? If it's normal weight, we'll say it's 1.0 and it's normal weight. If it's LWC, we'll also tell you that, right? We'll also tell you that. All right, so we have talked about the compressive strength of the concrete, the tensile strength of the concrete, relationship between them. And now let's get into the volume change. All right, now volume change is the biggest, right? Biggest enemy, right? When we deal with sustainability and durability. Okay, so what does volume change mean here in this course? We mean the permanent change of volume. It changes the shape, it changes total volume, and that can cause a lot of problems. For example, shrinkage, right? For example, creep, for example, thermal expansions. Okay, so we talk about them, right? What type of shrinkage, what type of creep, and what type of thermal expansions. Okay, so let's talk about them. Let's talk about them. So what is shrinkage, right? Shrinkage is shortening of concrete during hardening and drying under constant temperature. Okay, be careful. Okay, when we talk about shrinkage, we're talking about temperature independent properties. It's not related to temperature at all. Okay, so what's really happening is that as the concrete getting dried, the water goes out of it, right? Diffuse out of the concrete, you lose water, lose volume, you have shrinkage. And also, as the surface of the concrete evaporate, the water in the surface of the concrete evaporate faster than the interior. So you have exterior shrinkage. It causes exterior shrinkage caused by hydration is much more than the interior. And most important thing is that this will develop tensile stress. Okay, this will develop tensile stress. So what's going on, right? What's going on is here. If I can make a drawing again. So if I treat my concrete as a layer cake, okay, as a layer cake or like a filled donuts. All right, I'm a foodie. I don't pick a lot on food, but I love to use food as a analogy. Okay, so what's really happening is that you can think of the outer layer loses water faster, so it will reduce its volume, right? It will reduce its volume. So it tries to reduce, it tries to shrink, isn't it? So let me clear this out. It will try to, oh shoot, where is it? Eraser here. Okay, it try to shrink, right? So if I draw it, it will see a shrinkage sign here. Okay, so it will try to shrink. It will try to shrink. Okay, but now when they're trying to shrink, the inside core is kind of like a constant volume because the water is trapped inside. The water is trapped inside. So it is like a hard rock and the inside core and outside crust is trying to shrink. You will introduce a tensile stress on the exterior surface and then the exterior will crack. Then the exterior surface will crack. Okay, so normally you see cracking in the concrete and that can be induced by shrinkage. Okay, that can be induced by shrinkage. So shrinkage is bad, right? Shrinkage is bad. All right, so that is shrinkage. Okay, now shrinkage is also a time dependent behavior. Okay, it's not temperature dependent, but it's time dependent. So the beginning it shrinks a lot. As time goes by, it become more gradual, right? It tempers, so it does not shrink a whole lot. You see most of the shrinkage in the first 72 hours. Okay, you see most shrinkage in the first 72 hours, and you can confirm them from construction materials course. But that's when you see most shrinkages. Okay, and afterwards it just reduces. Afterwards, it just reduces. Okay, so that's about the shrinkage. All right, and shrinkage has to be controlled. All right, shrinkage has to be controlled. If it's not adequately controlled, shrinkage can result in unsightly or harmful cracks, which means the cracks you cannot see. All right, and it can sometimes introduce large and harmful stress in the statically indeterminate structures, which means if I have a bridge, for example, right, and my two ends, oh, sorry, my two ends of the bridge, for example, is fixed. Okay, you probably learned this from mechanics materials class. My both end is fixed. And then at this time, if the structure start to shrink, I will have a lot of tensile stress generated. And that is very critical for the structures. Okay, so these are pretty bad. And not only that, in terms of pre-stress, we apply pretension to the bridges, right? The shrinkage caused the volume reduction will negate some of the pre-stress I apply to the structure and defeat the purpose, right? Which defeat the purpose. So shrinkage is horrible, right? Shrinkage is horrible. And the last time is that how do we reduce shrinkage? We can simply add reinforcement. We can add reinforcement because reinforcement can take care of some of the tension caused by shrinkage, can save our structures. Okay, all right. So let's talk about creep. So what is creep, right? What is creep? So creep by definition is a permanent strain when there's a constant load applied. When there's a constant load applied. Okay, so let's explain a little bit. At beginning, if I apply a load to a structure, I instantaneously strain, and this strain is called elastic strain. This is called elastic strain. All right. So if the load is being maintained, is being maintained on the structure, right? I start to see additional strain. Okay, and this additional strain is not elastic, meaning they're not fully recoverable. Okay, and will keep increasing with time. Okay, and mind you that the magnitude of load applied to the structure does not change. It's still the constant load. Okay, once I remove the load here, take the load out, right? It will start to unload. It will start to unload in terms of strain, and this unloading is the elastic strain. Okay, is the recovery of the elastic strain. However, the creep recovery, as you can see, is small. It's minimal. So you were left with a permanent deformation, and this permanent deformation is called a creep. It's called a creep. Okay, so simply said, creep is a permanent strain caused by constant loading over a very long period of time. Okay, so that is the definition of creep. So creep is definitely bad, right? So creep can increase deflection with time, meaning if I have a beam, I have a bridge, and if I have a lot of creep strain in the concrete and the beam and the bridge will sag over time. Okay, and it will also cause redistribution of stresses because the shape change, configuration changes, the internal stresses will also change. And end of it also will decrease the pre-stressing forces. We talk about when we have a volumetric change, the applied pre-stress can be negated, which is bad, right? So these are the creep shrinkage, all right? And let's talk about the last thing is the thermal expansion. Truth be told, concrete can expand quite a bit, okay? And if you see summertime in the sidewalk pavement, some of the pavement can actually camber up, right? Cause a lot of disturbance. And those is caused by thermal expansion. You heat it up, it expands. Okay, and this has come from various factors. For example, the composition of concrete, which means you have a lot of water inside, heterogeneous property inside, and you also have an age of concrete. When the concrete becomes old, the composition becomes more heterogeneous, a lot of voids inside, so the thermal expansion changes a lot. Okay, so the thermal expansion is a big volumetric change for concrete structure. So you have to consider that when you design your bridges, especially when you have structural gaps, you actually have to design a thermal gap to allow it expand and contract. All right, so that's the thermal expansion. Now, some useful parameter to remember, okay, the coefficient of thermal expansion or contraction for normal concrete, okay, is at 5 to 7, 10 to the minus 6, okay, strain per degree F, okay, 10 to the minus 6 strain per degree F, okay, and this is for siliceous aggregates. If there are limestone and calcareous aggregates, different type of aggregates, okay, you can have a slightly different, okay, lower thermal coefficient, right? And then for lightweight concrete, this number is a little bit lower, 3.6 to 6.2, okay? But normally 5.5 is a satisfactory number we're shooting for in design, okay? Now, if you have concrete shipped to you or trucked to you from the Rolla Ready Mix or any ready mix factory that has been certified, you normally don't have to worry about this number, okay? And we usually don't test the thermal coefficient in the lab. Most important tests we do to the concrete are the compressive strength at 28 days. Some of the times we do 7 or 3 days, that's called early day strength, but normally we do 28 days. Okay, and then we also do slump tests, which is how workable the concrete are. We seldomly do the thermal coefficient test. Okay, all right, so let me close out this one. See my last few slides on the concrete properties. I think that's all, right? So that's about concrete. So once we understood concrete, we know that most of the concrete will utilize are the compressive properties of concrete. Okay. Now for reinforcing steel, right? Normally you don't see a very smooth bars. Okay. For the reinforcement in concrete, we always see deformed bars with ribs. Okay. Sometimes we have welded wires, and we also have pre-stressing steels. We have pre-stressing steels, and there are a lot of standards, right, for bars, especially for deformed bars where we use most time in the construction sites. They are ASTM A315, ASTM 706, ASTM 996, and these are all different specifications for different bars that to be used in concrete structures. Okay, and again, normally if we order them from the shop, they usually are certified, but you should know this. Okay, you should know this. All right, so how to read the bars, right? So when the bars arrive on site, how do we know these are good bars? I mean, how do we judge the properties of the bars? They're usually labeled, okay? They're usually labeled. So when you see a bar, you have these ribs, and these ribs will help you to enhance the bonding between the reinforcement and concrete. And you can also see letters or symbols, right? The first letter or symbol usually representing the mill that the bar is coming from. Okay, the following numerical number is the size of the bar, which is critical, and we'll talk about it. Okay, and then the letter following the number is the type of steel. Okay, so bars marked with S and W meets A615 and A706. Okay, and some of them also have the great lines. Okay, great lines. And there's also another important factor. If I have a hexagonal shape of deformed bars, I also have the grade marked here. Now, 60 means the yield strength of the bar is 60 KSI. Okay, and we talk about this. We'll talk about this. All right. So bar size, okay? So when you go to the job site, people will not refer to the bars with diameter of 0.375 inch, diameter 0.5 inch. No, they'll just call the number, right? They call it number 3 bars, 4, 5, 6, etc., so on and so forth. Now, there's a correlation between the size and the area and the diameter of the bars, okay? So if you pay attention, this is number 3, meaning it's actually have a diameter of 3/8. Okay, so this is 3/8. So by every size increase, right, it's an increment of 1/8. So here is, sorry, let me erase here. So this is not 3/8, this is half of it, right? This is half of it. Okay, so this is 4/8, right? This is 5/8, okay? And this is 6/8. So every number increase, right? So it gives you by an increment of 1/8, increment of 1/8, right? So number 8 bars, 1 inch. So these are the diameter, right? These are the diameter. So this is ½ inch, and this is 5/8. So it's points. So, oh my God, sorry. My drawing is horrible. I need to change my, okay, anyway, let me erase it. I need to change my drawings. So this is 5/8, and that correlates to the diameter of the bars. Okay, all right. Okay, so that's how we label them. That's how we label them, right? So the number is related to the size of the bar. Numbers related to the size of the bars. And you see all these size of bars, right? And we have different utilities, different usage for these bars. So normally we can divide them, right? Normally we can divide them by groups. So these number 3 or 4 or 5, okay, these are good for stirrups, okay? Transverse reinforcement for shear, okay, for shear. And 6 all the way up to here, these are good for flexure, bending, that is, flexure, and also for axial compressions, for column, that is, okay, for beam and column. Okay, so some of the slab use number 6 as well, but very few. And some of the slab use number 7, number 8 as well, but very few. So this might be a good for slab structures. Okay, so these are the typical usage for bars. And again, we'll talk about them. We'll talk about them when we get to it. Okay, when we get to it. Now, last but not least is that the area of the bars. The area of the bars. Okay, now these are the typical area bars. I have seen a lot of students, sorry, use this diameter to calculate the area, cross-section area, and they usually come up short because there's a loss of the cross-section area due to ribs. Okay, so pay attention. The cross-section area of the bar is not pi d squared over 4, okay? It's not pi d squared over 4. So you might have to remember these numbers, okay? So if you do not know these numbers by heart, you can always find this table in appendix table A5 in the textbook, okay? Table A5 in the textbook, all right? Okay, so these are the bars. So what is the tensile behavior of the steel reinforcement, right? So now I plotted the stress versus strain curves for the steel. So initially follow a linear relationship where ES is the Young's modulus, right? And now once it goes up to a certain point, I achieve the yielding, which is the yield strength of the bar, which is Fy, okay? And afterwards, I have a little bit peak. I increase gradually to reach my second peak, and when there's a necking developed, I can have a stress reduction and eventually to failure, okay? As a solid line depict, okay? However, in design, we do not rely on this complex solid line, okay? Instead, we're using the dashed line, which is very simple. It's called elastic, a straight line, and plastic, a horizontal line. So 2 segments behavior for the tensile behavior of the bars. Okay, so essentially the stress in the steel reaches to a yield strength, which is Fy, and then stay there for the rest period of strains. Okay, for the rest of the period of strains. So that is a simplified, the dashed line is a simplified design property for reinforcement. Okay, all right. So talk about the yield strength of the bar, right? Yield strength of the bars. Okay, and these are related to the grade of the steel. Okay, so typically we have 40, 50, 60, 75. This number representing the yield strength of the bar. So grade 40 have a yield strength of 40 KSI, 50, 50 KSI, 60, 60 KSI, 75, 75 KSI. Very rare, almost never, we will see a yield strength over 75. Okay, most of the yield strengths for beam and for columns are in 60s and 75s, and most of the yield strengths for stirrups also 60. But some cases for very nominal reinforcement, very low level, we have seen grade 40. But most cases we see 60. So let me label this. We see 60 and 75. These are most common grade we see from steel. Okay. All right. So that is the reinforcement. That is the reinforcement. Okay. So let me pause here and to see if you guys have any questions for me before I start the next chapter. So guys, anything for me? Anything? Are we all good?
Have you posted the slides that you just went over?
Yeah, I did already. Chapter 1, 2, 3 already on Canvas.
Okay.
Yeah. So check it. If it's not there, let me know. Okay.
Yeah, it's there.
Okay, sure. So any other questions, guys? Is there any question about the concrete properties and steel properties? Okay, so before we move on, let me quickly recap, right? There are critical things we need to understand for concrete properties. So if you don't mind, I'm gonna share my iPad screen. So I'm just gonna write a quick note on it, okay? Again, I'm not going to force you guys to remember, and nor these notes are critical, but I just want you guys to have a quick understanding or like a summary for this. So let me share this. Okay. Okay. So I'm sharing my iPad screen, and let me know if you cannot see it. Okay. So now let's talk about this. So we have talked about the concrete compressive properties. Okay. So there are a lot of remember, right? Shrinkage and all these and all kind of stuff, right? But most important thing for design are F prime C. Okay. This is 28-day strength. Okay. Using compressive cylinder. Okay. Knowing that. And second is modulus of rupture and how we calculate this. Okay. So think about it. We have a bending of beam like this and something like that, right? And that's the bending moment here, and that's how you calculate the modulus of rupture, right? And also know that modulus of rupture is roughly equal to 7.5 square root of prime c. And again, don't forget lambda, right? That is lambda equal to 1.0 normal weight concrete, lambda equal to 0.75 lightweight concrete. Okay, and also we know that FCT, which is the split cylinder tensile strength. Okay, tensile strength. If you have a hard time of spelling out like I do, you just remember in your head that is a cylinder. I have a horrible drawing, but it's a cylinder being split down in the middle. Okay, down in the middle. Okay, so this, remember that is smaller than FR, smaller than FR. Okay, so these are the three critical things you need to remember about the concrete. So how about steel? How about steel, right? So I need to know first that the reinforcement or the stress strain reinforcement, stress strain of the reinforcement follow a straight line and horizontal line. And this is called the yield strength Fy. All right. And this is called the Young's modulus of steel. And I haven't said so, but the typical Young's modulus for steel is 29,000 KSI. Okay. Remember this. 29,000 KSI. All right. And now Fy is called yield strength of the concrete. Sorry, yield strength of the steel. That means when the steel yielded. And that is related to the grade. So grade 60, 60 KSI. Okay. And grade 75, that means yield strength is 75 KSI. Okay. All right. So again, if I have a number 3 bars, the diameter of the bar equal to 3/8 of inch. If I have a number 4 bars, okay, the diameter is 4/8, okay, so on and so forth. All right. Now, my personal favorite is number 9 bars. Okay, number 9 bars. Why is that? Because the diameter of number 9 bars is only 9/8. Not surprising, but the cross-sectional area of number 9 bars equal to 1 inch squared. Okay, so it's very easy for me to count how much of area I can provide for number 9 bar, right, per bar. Okay, so these are something that I think is critical for the design process. Okay, I'll upload this note to the Canvas, you'll have it, but these are the critical information you need for the basic properties of the concrete and steel. Okay, all right, so any questions for me on this? Anything for me on this? All right, okay, well, if nothing else, let me quickly move on to design a little bit. Like I promised you guys, I'll get you out of here before 2:30, okay? Let me see. Question H, how long does class last today? Oh, I posted a note, we'll get you out of here around 2:15, so 15 more minutes, so just bear with me. If you're getting tired, you wanna get a glass of water, be my friend, be my guest, you can always check back on the YouTube, you know, if you miss anything, and you can find them from recording, okay? All right, so let me start sharing the screen again. How do I do that? Okay. See, how do I? Okay, so let me go to Zoom, share screen. Now, I'm sorry, folks, the Thursday class is usually a little bit longer. I'll try to keep it short, but I just want to cover enough material so won't be behind, okay? All right, so chapter 3 or last chapter of the introduction session of the course is the design process, okay? Is the design process. Basically, how we design reinforced concrete structures, okay? Of course, the reinforced concrete structures is very complex design, okay? The design code is very complex, okay? So as code for all constructions. So as code for all constructions. Matter of fact, because it's a safety issue, the design code has been held sacred for a very long time. Now this is the Hammurabi code digged out on a tombstone, basically 1790 before century. And it says that if you build a house for someone and does not construct it properly, and the house which built fall in kind and kill its owner, then the builder shall be put to death. So it's pretty serious, right? And if it kills the sons of the owner, the son of that builder shall be put to death. So it is very, very important. So for us civil engineers, the building code is the Bible, is everything we're working towards, right? To make sure our structure is safe and sound. Okay. All right, so here's a critical question. It's a simple one, but yet very few thought has been given to it before you know the design courses. How do we design, right? What is the design states, right, we're shooting for? So there are three. One is called ultimate limit states, okay? And the second one is serviceability limit states. And the last one is special limit states. And for some of the smart ones in the class, now knowing that we're going to have exams, and these three might be the answer to the question that are going to show up in the first exams. Okay, that's all I'm saying. All right, so this is for the limit states for design. So first, let's talk about this ultimate limit states. So what is ultimate? What does the word ultimate mean, right? The word ultimate means loss of equilibrium. Okay, loss of equilibrium means that the structure is no longer stable anymore, it might fall, all right, because the force is now being balanced out, right? And the second is rupture, when the member cracked, fractured, loses the capacity to resist the loading, okay? And the third one's progressive collapse, right? When one section of the member loses strength, and domino effect will cause the next member loses strength, and so on and so forth, okay? Number four is the formation of plastic mechanism. Okay, what does plastic mean? Means that especially the joint, when it hits the maximum capacity, it cannot take the resistance anymore, but will stay there, right? So the whole structure joint acting like a plastic hinge will take the load, but cannot exceed that load. So that is called a plastic mechanism. And there are also instabilities when you have a steel column come like easily to come down and buckle, right? That's the instability. And last but not least is fatigue. Fatigue. What does fatigue mean? Means that if the structure is susceptible to thousands of cycles, it may eventually fall down. So that is the fatigue loading. Okay, that is the fatigue loading. All right. So what is the serviceability limit states? Serviceability limit state means that the structure, even if the structures are sound and still safe, but there are serviceability deterioration happens, and these are called serviceability limit state. For example, excessive deflections, right? If the bridge sags so much, it's not safe anymore because the cars travel on them no longer can have a safe ride, right? Smooth ride. And also excessive crack width. When I see a structure have a lot of cracks and the water can goes into it, can eat into the steel, and that's bad, right? So we don't want that happen. So that's the serviceability limit state. And last one is undesirable vibrations. Of course, if you ever climb up to the top of the St. Louis gate, right, the arch, and you sit on top of it, even the wind can push the arch coming back and forth and vibrates, and that does not give you a safe feeling, right? So undesirable vibration can also be a service limit states. All right. The last but not least, the special limit states. For example, the damage or collapse due to earthquake. So you need design your buildings for earthquake in some regions. For example, like Sergio mentioned in the last class, in Mexico, there are a lot of earthquake, right? In our California region. And actually, some time back in Missouri, there's also a North Ridge earthquake zone where we have the design corresponding to earthquake activities. All right. And also damage or collapse due to explosion, fire, or collision. For example, the oil tank, oil industry infrastructures, pipeline structures, and for anti-fire buildings, and for collisions, for example, bridges have the side that can be hit by vehicles, and those things has to be designed for. All right. And the third one, the structural effect due to corrosion or deterioration, especially in the northern part of the country where there are a lot of rust. Sorry, there was a lot of thaw and freeze cycles when we see a lot of salt, de-icing salt gets into the structures, and those structures can deteriorate pretty fast. And last but not least, the nuclear issues. For example, like nuclear safety shells, when we create a concrete structure to enclose the nuclear reactors and the radiations and the possible explosions, the implosion might happen in the structures, and those are need to be considered. And this is calling for the special limit states, which are different from the strength and serviceability limit state design. All right. Now, because we have so many different states, this course we're talking about right now focuses on the strengths, okay, on the strengths, which is ultimate, okay, ultimate design limit states, the first one. All right. We touch upon slightly on the serviceability, but not a whole lot. So in terms of strengths, right? In terms of strengths, there are two types of strengths. One is called member forces, basically the intrinsic strength of the beam of the column, right? In terms of how much bending moment can it take, how much shear force can it take, and that is called the member forces. And the other category is called composite action. When I have a concrete beam sitting on a steel deck, when I have a steel beam sitting on the concrete columns, how does the structure etching together? How does the connection work? Those called composite actions. Okay, so here again in this course, we're focusing more on the member forces. That is specifically the flexure, which is tension control, which means the bending of the beam or the bending of the column. Okay, and fail in tension. Okay, so it's called tension control flexure failure design. And also shear, how a beam might shear in two pieces, right? So there's a shear limit state design. And last but not least, for a column, we might have axial forces, which means compression along axial directions. And combined with axial flexure means I have a bending as well, right? And first thing easily you can imagine in your head is I have a load a little bit off center of the center of the column that while you're compressing it, you also cause a bending to the columns, right? So these three are the most common case we're designing our structure for, okay? Common case we're designing our structure for. Now, of course, right, we talk about strength design, we have to talk about strength design requirements, and we have to talk about analysis methods. So these two concepts are different. What is strength design requirement? Basically, what type of load, okay? What type of load that you're expecting on the structures? How do you calculate them? And the other is analysis method. That is, if I provide so much geometry, like sections, and so on, so concrete, and so on, so configuration or reinforcement, what is the capacity of the members? What is the capacity of the members, right? So you think of it, it's more like left-hand side is a load, right-hand side is the design capacity. I have to make sure my design capacity is bigger than the applied load, right? It's bigger than the applied load. So how do we calculate them? And how do we know that? We refer to the ACI 318.19. All right, and the commentary. So if you haven't made a purchase or haven't gotten access to it, please do as soon as you can. If you have a trouble, let me know now, because in the first exam you need it, and I doubt you can borrow it from anybody else, okay, but yourself. All right, so make sure you have access to this. All right, design standard, which is ACI 318.19. All right, okay, let's quickly talk about the strength design requirements. What are the requirements when I design a building? Okay, so the strength requirement simply says the design strength, okay, design strength has to be larger or equal than the required strength, of course. Okay, larger or equal than the required strength. So what is design strength? Design strength is the strength reduction factor phi multiplied by the nominal strength, right? What does it mean? It means that I design a section, and for example, the section can take a moment, for example, 100 kip foot. But I need to consider other factors. For example, if the material is the materials I wanted, if there is any human error happen in the fabrication, or if there's any stress-induced variations to the structure member. So you have to pre-multiply a strength reduction factor. Basically, expect that the calculated nominal strength cannot be fully reached. Okay, so that is called design strength. So you reduce the calculated analysis-based strength. All right, and then you compare that to the required strength, which means is the service load effects, which is how much pound per square foot you apply to the buildings, how much moment you exerted to that member, but with a load factor usually higher than 1.4, 1.6 to magnify it, to increase that. Okay, so essentially the game is that to boost up, right, to increase or multiply higher, right, to get a higher service load and to reduce your design strength and still make sure that your design is larger than the required, then you're safe. Okay, then you're safe. So there are certain safety factor design. Sorry, there are certain safety factor already considered in this design approach. Okay, in this design approach. All right. So load or resistance factor are necessary. Okay, are necessary, which means it is necessary to increase the expected loading. Why is that? Because it have a lot of variabilities in the resistance. For example, the concrete material properties. Yeah, it's testing a cylinder maybe 4,000, 5,000 psi, but in the structure maybe there's a hole in it, right? We have air pocket in the beam, so it's not that high, right? For example, there's a loadings, right? When we say the wind load might hit us like 10 kilometer per meter, but maybe higher than that. Maybe that day we just have an unlucky day, isn't it? And we also have a consequence failure, right? So if I have a fence structure nearby my home on my deck, right, or on the first floor, it's not a big deal, right? I just have to buy more lumbers, all right? Worst case scenario, I just buy my wife a different size of beams to make her happy. But if this is a beam in the structures, right, in the bridges, right, in our residential buildings, right, in our offices and hospitals, the consequence failure is much higher, isn't it? So we cannot allow any failure, right? So then we boost up, right? We boost up the applied loading. Okay. All right. Again, there's a typo here. Apologize for it. It's ACI 31819, supposed to be 19. Okay. So there's a definition. Still, section is correct. 21.2.1 is on the strength reduction factor. Okay. Now, following are the 4 important reasons why we apply the strength reduction factors. Okay. You need to remember these because some wise one said this will appear in the first exam. Okay. Some wise one says this will appear in the first exam. All right. So the strength reduction factor come from A, under strength of a member. Okay, under strength of member means the member is being undermined, it's not taking as much strength as we designed it for. Okay, some accident might happen. Okay, and the second reason, inaccuracy in the design equations. Okay, you say, Bob, how come, right? You're teaching us the design equations. How come the design equation is not accurate? Well, keep in mind that all the design equation we're utilizing mostly from empirical relationships. Okay, what does empirical mean? Meaning that they mostly come from experimental results. Okay, not pure theoretical result, but experimental results. So there are the variations in the design approaches and equations. Okay, and the third one is the degree of ductility and required reliability of the loaded members. Okay, degree of ductility, what does it mean? For example, if I have a beam that fails, I rather it fail in a gracious manner, meaning if it fail in a day, gradually, I have time to run, right? That means ductility is good. But if I have a member that fails in a brittle fashion, right? Before 1 second before it's still intact, and the next second it break in half, that gave me no time to respond, and that is called a brittle failure, right? So the higher ductility it is, the higher strength it is, the lower strength reduction factor I'll apply. Okay, and the second, required reliability of loaded member, right? For example, if I have a bridge, I have support and I have a major beam across it. So the beam member has 100% importance of the structure, right? The support is less critical, right? Is less critical, right? So there are different reliability of the loaded members. And the last one is the importance of the member in the structures, right? If I have a frame, for example, I have a joint, I have a beam, I have a column. So joint is very critical, right? The joint in the frame structure is very critical, right? So strength reduction factor is determined based on these 4 factors. Again, the wise one said, you need to remember this because in first exam, you see a problem like this, probably worth 10 points, okay? So be careful on this, all right? Okay, now, These stress reduction factor has numerical values, okay? Has numerical values. And these numerical values are assigned in the code section 21.2.1, and we talk about them in detail later based on the type of failures. If it's tension controlled failure, okay, we'll tell you this, and it's 0.9. If it's compression controlled failure, it's 0.75. You see there's a spiral in it, in the bracket, right? Spiral means spiral shape stirrups, okay? If I have confinement, spiral confinement, okay, this is 0.75. If I have a compression controlled failure, other usually means rectangular ties, right? Rectangular tie stirrups, I have a lower number, you see, because spiral offers better confinement than the rectangular ties. We'll talk about them in the column design section, okay? So it's a lower number, 0.65. And number 4, if the member fails in shear or in torsion, is 0.75. And last but not least, if it fails in bearing, well, what is bearing, right? When I have a beam sitting on the column through a pad, and that locally generated stress will crush the column and may causes bearing failure. So when I'm expecting a bearing failure, I have a 0.65 as a stress reduction factor. Okay, that is the stress reduction factor. All right, so nominal strengths, all right, nominal strengths. So we need to actually calculate nominal strengths of the member first before we apply the stress reduction factors. Okay, so how do we calculate the nominal strengths? Usually that's a cross-sectional strengths calculated using assumptions, right, from the strengths design methods in the ACI code, which we will elaborate. Okay. All right. So strength requirements, right? We need to have load factors, right? We need to have load factors, meaning that when I have a load applied to the structure, I need to pre-multiply a factor in front of it, and that becomes the design load. That becomes the design load. Specifically, there are different load types that give you the different factors, right? There's a dead load, okay? There's a live load. There's a roof live, there's snow, there's rain, when seismic, soil, fluid, temperature creep, shrinkage, you name it. All right, so one by one, what is a dead load? Dead load is a permanent load applied to structures, include but not exclusively includes the self-weight of the materials, okay? The facility that permanently fixed to the structures, right? For example, some of the steel shingles, and those are dead loads, right? And what are the live load? Live load means humans, right? We sit down there, we come and go, right? And furnitures, sometimes we have this furniture, sometimes we have that furniture, right? And roof live load means when I have a people walk on top of the roof, when I have some equipment, for example, solar panels might be on the roof, semi-permanent loading, roof load. Okay, and what is snow, right? Snow, you have precipitations, you have to consider snow loading, right? Rains, the same thing. The wind, right? When I have a windy area, I have lateral forces. Seismic zones have seismic forces. Soil, right? When I have a settlement in the ground, I have a different loading. Fluid, when I have waters against my bridge piers, I have different loadings. And when I have a temperature, thermal expansion related loading, creep loading from the materials, and shrinkage loading from materials, especially in a slab, right, where I have a temperature which is critical, I need to consider these different type of loads. All right, and by now you must be confused, right? Confused very, very much, right? You say, where on earth can I find these, right? So you can simply refer to a different code, right? This is the minimum design loads for buildings and other structures, ASCE 7-16. You will find all the answers in this tiny book, okay? But we don't have to worry too much about it in our course because we do we do things simple, right? And again, apologize, should be ACI 31819. I should have changed it last night, forgot, sorry about that. And these are the correct combination of loading in the ACI 318 codes. Okay, on the left-hand side, the symbol U representing the ultimate loading, okay? And the factor 1.4, meaning that is 1.4 times, bracket inside dead plus F means dead load plus what is F here? What is F here? F is the seismic, sorry, F is the fluid, right? Fluid. I have other combinations, 1.2, 1 plus 1.6 plus 0.5, I have 1.2 dead plus 1.6 points plus something else. all these equations, right? All these equations are very confusing, right? So how do we apply these equations, right? How do we apply this equation? So let me stop sharing and let me explain. Okay, let me explain. So how do we apply it? Goes this way. Let me give you an example, right? Let me give you an example. So okay, all right. So first thing first, all we care about, let me repeat, all we care about in our class, right? In this course, all we cared about are two things, the dead load and the live load. Others, not so much, right? Not so much. So we always say that the ultimate load, okay, I use big U here, ultimate load equal to 1.2 dead plus 1.6 live. All right, that is the most often seen combination. Sometimes we have 1.4 dead, and that's it. That's the two combination you're gonna see most from this class. All right, so you will see from a similar problem like in the homework, say I have a beam and simply support it. Okay, and I have applied load here, P. All right, I say P equal to 8 kilo, well, let me use US system, 8 kips. Okay, and I have a span length of L equal to 20 feet. So L equal 20 feet. All right, and out of this 8 kips, right, this is so-called the dead load. All right, I'm just making things up, okay? And I also, on top of that, I also have a PL, which is which is live load, and let's say live load is 10 kip. Okay, and I will ask a question because now I have in the middle span here, and I know the moment diagram will look something like this. And if you forgot about moment diagram, you may want to review a little bit. And I know that the moment caused by this by this concentrated force equal to PL over 4. P is the applied force, L is the span length, 4 is just division, right? Because it's half span length. And whatnot, this is the moment, okay? This is the moment. All right, so the question is, I apply a dead load of 8 kips, live load of 10 kips. All right, if I say I'm going to use U equal to 1.2 dead plus 1.6 live, what is the design load at middle span? What is the design load at mid span? Matter of fact, what is the design moment? Oh, sorry, shouldn't say design. What is my ultimate moment? Ultimate. Okay. What is the ultimate moment at the middle span? Right. This is similar to your homework problem. So how do we solve this? How do we solve this? Okay. So here, I know that dead load gave me a moment MD equal to PD multiplied L over 4. Right. So that means 8 kips multiplied 20 feet divided by 4. So turns out to be 40 kips foot, right? And the live load ML is P live multiplied by L divided by 4. So P live is 10 kips multiplied by 20 feet divided by 4. Okay, so this gives me by 50 kips foot. Okay, now I'm asking what is the ultimate moment? So MU use that combination here equal to 1.2 dead load plus 1.6 live load. All right, so that gives 1.2 multiplied by 40 kips foot plus 1.6 multiplied by 50 kip foot. Okay, so this is 48 and this is 80 kip foot, and I have 128 kip foot. And now this is ultimate load or ultimate moment applied at the middle span. Okay, this is the answer. All right, so can you see it? So can you understand how to do the design ultimate load for the structures? Any questions, folks?
Made sense?
Okay, good. All righty. Now this is just a simple example, right? So I urge you to think if you have a distributed load like this, say omega d, and I give a number later in the homework, and I have omega L, and I'll ask you what is the mu at the middle span. What you do? You decompose this into a structure that only have the dead load sitting here, and you calculate the moment distribution by that, right? Probably something like this. And then you also compute the moment caused by the live load, right? Get a moment distribution of the live load, right? And we're here at the middle span. This is MD at middle span. This is M live at middle span. So your applied or ultimate moment at the middle span should be 1.2 MD middle span plus 1.6 live middle span. Okay. All right. Use the superposition method to do this. All right. Okay. Now this is entirely new to us. I think it will take you several runs to be familiar with the process. So give a try tonight when you have the homework, and urge you do not drag it. All right. If you say, it's due next Thursday, let me start next Tuesday, and that's already early. No, you have troubles. Trust me, you have trouble. By experience, I know that's going to have problems with it. So start today. Okay. If you're smart, you take a look at, I understand, right? Run some example, you can finish it, okay? Then you can take your weekend off. If not, work it over weekend. Ask me questions next Tuesday in office hour. Okay. All righty. So that is critical. I'm so happy I got this done, so I don't have to worry about it. Okay. Okay, so let me come back to the course content. Where is it? Here. All right, so this is the strength requirement, okay? And then quickly, that's the factor moment. We just talked about it. Factor axial force, similar method. Factor shear, similar method. Factor torsion, similar method. Right? And on the other hand, right-hand side, which is the nominal strength, right? When you calculate for nominal strength, we have to get the sections. The whole thing is that we have to satisfy this equation, which means the strength reduction factor phi multiply mn, which is multiply the nominal strength, has to be bigger and equal than mu. Mu is the applied moment, like I just showed you how to calculate. All right, so this is the gist of design. All right, if nothing else, remember this approach. Okay, if nothing else, remember this approach. Where did you get 8 and he made it? Yeah, I definitely made it up. Okay, just some arbitrary number. All right, you can swap those numbers with whatever you want. All right, but please use your homework as a practice. Okay, if any question, email me. Okay, all right, folks, that's it. That's it for today. Usually every Thursday takes about 1.5 hours, a little bit long. So, if I were you, get some coffee on the side, water on the side, and be ready. And don't worry if you miss anything, you have to go to the restroom for, because it's all recorded and you can come back and see it. All right. Okay. Is there any question for me for this? Guys, any question for me for this? Hello? Anything? Are we all happy about it?
Not at the moment. We're good.
Alrighty, good deal. Like to hear that.
Are there any? When is the first exam going to happen?
Oh, we don't know yet. I think we're gonna know that in a couple of weeks. Okay, because I need to schedule it, and I want to find out, are we gonna do online or we're gonna do in person? Most likely gonna be online for the first exam, but I need to verify that in 2 weeks.
Will the exam be open book, open note, or closed book, closed note?
Probably gonna be open, to be honest with you, but trust me, it won't help. We've been doing that in the last semester. I don't think it will help you. Actually, it will slow you down. So if you do homework all right, I don't think you need that a lot in the first exam, okay?
Okay.
Yeah. Anything else, folks? Any questions about today's content? Anything? All righty. Okay, so if nothing else, I'm gonna close it, and I'll upload the notes, including the PowerPoint. The PowerPoint is already there in terms of PDF, and the written notes I also upload today, okay? So you see them in the file folder, If you have any question, email me or see me next Tuesday. And let me remind you again, do start your homework today, okay? If you delay it, it's gonna be your own fault. You'll regret and you'll cry to me later, okay? So try to start today, all right? Thank you all very much, and I will see you on Monday.